Hello. Okay. Hi. Hello, everybody. My name's Cisneros. I guess we'll get started here. So I'm a cryptographer with Semiotic Labs. We are core devs of the Graph protocol. And today I'm going to be talking about ZK-Coprocessors. And so just real quick to get a feel, who has heard of a ZK-Coprocessor? Okay, a handful of people. Nice. So my goal with this talk really is to kind of just talk about them at a high level. So for those of you who haven't heard about them, hopefully you'll come away with an understanding of what they are and how they fit in this blockchain context. And then I also want to talk about, so we're working on the Graph protocol. I want to talk about how the Graph protocol can use ZK coprocessors or be used as a ZK coprocessor, and the things that we're kind of planning for this coming year to build on top of it. All right, so let's go ahead and get started. Okay, so up first, just to get a feel of what coprocessors are. All right, so anybody know what this is? It's Intel 386, so an early 90s processor, very popular, but it couldn't do floating point arithmetic very well. And so then they invented the i387, which is a floating point unit, a coprocessor, which would supplement the 386. And so basically the 386 would offload floating point arithmetic to this 387. And then when the 387 would do its computation and then feed it back to the 386. And then the 386 could do stuff from there. So that enabled all kinds of things, right? So that enables scientific computing, that enables statistics calculations, all kinds of good stuff could be built now with this system. Now here's another example of something that uses a coprocessor. So this is a smart card. A lot of these smart cards, they have a little microcontroller in there that is used to handle I/O from a card reader and the logic of the card. A lot of them also do cryptographic signing, right? So they'll, elliptic curve signing of messages you use to authenticate with that card. Cryptographic operations, for a lot of us we know here, they're pretty heavy duty, right? Doing modular arithmetic with large numbers, you can't do that on a microcontroller with any reasonable time. You'd be sitting at your terminal for minutes waiting for your transactions to finish. So they invented, a little crypto coprocessor. This is alongside the microcontroller, and you can offload signing and all that stuff to that crypto coprocessor. And again, another coprocessor, right? So the GPUs. And so the point of this is to show coprocessor is a broad definition, right? There's we had floating point units, we had modular arithmetic units, we have graphics processors. It covers a big space. It's a broad definition. They all kind of have one core thing that they do, and it's that they accelerate the performance of the system that's managed by the CPU. So that's kind of the core piece of a coprocessor. It accelerates. And so now let's get into blockchain. So the blockchain, as we know here, it's a new kind of computer, right? It has different strengths and has different limitations. And so it also needs a coprocessor, right? And so now we have a blockchain coprocessor. It's a new kind of coprocessor to offload computation from the blockchain. And then I highlight here, we're talking about blockchain coprocessor first, not directly jumping into the ZK coprocessor. And there's a reason why I'll get into. And so now to try to build some intuitive understanding of what a blockchain coprocessor is doing, let's assume that this balloon represents all of the computation that you need your smart contract to perform. So you need some result from some computation, and this computation is a big, heavy-duty computation. If you do all this computation in your smart contract, you're going to be spending a lot of gas. Right, so big computations, big gas, very expensive, and you may not even be able to get it done. So enter coprocessors, blockchain coprocessors. So a blockchain coprocessor, we introduce some little extra muscle, so the hand squeezing, a proving system, for example, and it kind of distorts that computation. So instead of all the computation having to be done in your smart contract, we can now kind of shift the computation around, and so now we can have these coprocessors, which are doing the computation. And then we have, within our smart contract, maybe just some little piece of computation that just verifies that what the coprocessor did was correct. So kind of to build these analogies, a coprocessor accelerates CPUs in normal land. A blockchain coprocessor saves gas. That's the whole point of it. So you have broad definitions, everything's a coprocessor. The key piece is coprocessors save gas. Okay, now for a little more less abstract example. So here is your computation without a blockchain coprocessor. You've got your smart contract, you've got some expensive computation or expensive calculation that you need to be run. You've got your input, and then you get your output. And then whenever you want to use this, you make your call to your expensive calculation with your input. Costs a bunch of gas because it's a big heavy-duty computation. And then you get your output, and you do something with it. In the blockchain coprocessor situation, you have a different, something different gets executed in your smart contract. So instead of doing your big, expensive calculation in the smart contract, you just do a cheaper operation, verify expensive calculation. And this takes in kind of 3 inputs now. So instead of just passing your input all the way in, you also take your input, your expected output of the calculation, and then some proof that this was done correctly. And then your verify expected calculation returns some little flag, says is valid, so input does equal output, and the proof says that it does. And then you can use that to do something, right? So kind of the flow off chain, you have your prove. So your prove is proving that your output equals this expensive calculation on your input. You get your proof. Then on chain, you run verify expensive calculation on your input, your output, and including your proof. And then if it returns is valid, do something without. So you get kind of you get the same result. You still get to do something with your output, but you get to save big on gas by doing this expensive calculation off-chain and then proving it somehow. Okay, so now blockchain coprocessors. What is a ZK coprocessor? Why differentiate ZK coprocessors? And so this gets into kind of like one of the core things that we do with blockchain, right? Like trust is one of the biggest pieces that we talk about. So ZK coprocessor, the distinction comes down to like who do you trust? And so now we got to talk about trust assumptions, right? And so I've kind of like outlined like 4 high-level trust assumptions that I think kind of exist in our space, right? And we kind of use either implicitly or explicitly. So kind of like the strongest trust assumption is basically trust in authority, right? So you have one central authority, whatever they say is truth. And so you could use, in your blockchain coprocessor, you could have a blockchain coprocessor that is built off of like an authoritative trust assumption, right? So here, in that case, your proof, rather than computing any type of proof, it would just be the authority signs output is expensive calculation. It is correct, right? So they sign it, they say it's correct, your proof is the signature, and on chain you just verify, did this signature come from that authority? Similar things, right? You have quorum, right? So this is M of N trust, so like kind of threshold trust. This is kind of like a multi-sig, right? So you can imagine, DAOs, that kind of thing. You have a group of people who you get trust at least half of them, or at least some threshold of them are going to be honest. And so then you could do a similar thing here, right? They all sign a message, aggregate it, on chain you check, did at least M people sign this, then you're good. Optimistic, it doesn't quite as fit as well in here, but you get a similar thing, right? You have one of N trust assumptions here. And then trustless all the way down here, this is the holy grail, right? This is why people love snarks, because you no longer have to trust anybody, right? So now your proof here becomes a literal proof. It becomes a ZK proof that your calculation was done correctly. And so that's the holy grail, right? And so really, that's my, I like breaking it out this way and talking about blockchain coprocessors kind of abstracted, because I think they fit, and there's valid situations where you could use each of them with these assumptions. So there we go. So now we've talked about blockchain coprocessors, we've talked about ZK coprocessors, trust assumptions. So what are people doing with this, right? What are people building with blockchain coprocessors and ZK coprocessors? And so the first one I lay out here, this one is kind of this maybe just more of an observation, right? Or maybe a retcon, saying layer 2s are kind of blockchain coprocessors, or maybe they're more correctly, they're using blockchain coprocessors to prove the state transition function, or the execution of a bunch of transactions in a block. And then outside of that coprocessor, outside of that proving, then they have some logic for handling, sequences of transactions, and then for like updating state in the layer 1. So layer 2s, that's I think a good example of where ZK coprocessor is being used. More explicitly, where the ZK coprocessor word is being used, is kind of like two big places that I've seen. So I've been to kind of surveying, trying to track who's doing what. These are kind of like the two big ones that I've seen. One is like scalable computing, right? So like literally taking your big computation, doing it off-chain, making your proof, and then verifying it on-chain. And so the use cases here that I've seen the most are this AI ML. And so for example, like Modulus Labs, they have a setup where they're using snarks to prove, this is like literally one of the things that they're doing. They're using snarks to prove an appraisal price prediction from a machine learning model. I think they're like a gradient descent algorithm. And they're attesting to that proof on-chain, right? So they're generating snark proofs, attesting the proof on-chain, and then they have kind of like a snark-proved prediction. The other big one is related to historical data. So retrieving historical data from a blockchain and proving that that data was correctly, or was actually committed to on the blockchain, right? So this is kind of like, you think of events get emitted from your contract executions. You can only track like blockchain data back like to the past 256 blocks. So if your data is older than that, you're not going to be able to directly access that data from the EVM. So you need some way to prove that this event was actually emitted. And to do that, we have inclusion proofs, Merkle inclusion proofs to a block. And then you could batch a whole bunch of these together, make a snark that all those Merkle inclusion proofs are correct. And then now you can use that snark proof on chain to say, oh, all this data was committed to on the chain. And so, so we see that in storage proofs. And then when people are doing computation on those proofs too. So not only do you prove this data was on chain, you also do some computation on that data and you prove that that data was done correctly. And I also have privacy down here. And I have some question marks on it because I just saw it and I didn't have enough time to dig into it, but it's really interesting, right? So ZK, the true ZK is zero knowledge. All these other things are like the snark part of ZK snarks, but privacy is the thing that gives you anonymity, gives you the ZK piece. And so this is just a chart of the companies that I've seen, and I'm sure I'm missing some, and I'm sure I'll meet some people here who are also building this. But this is kind of like where people are kind of lying, right? So we've got the AI side, we've got Modulus Labs, who are doing some pretty amazing stuff there. We got Giza, Ezekiel, who are building like AI proving infrastructure. They got Space and Time and Aura, who are doing both AI and also proving computations on historical data. And you got Axiom, who kind of kicked off the whole ZK coprocessor meme. And then these are guys, Lagrange, Herodotus, Brevis, they're all kind of doing similar stuff with historical blockchain data. Then over here we have infrastructure level. So here we got like Bonsai by RISC-0, which is a big scalable RISC-0 ZKVM. Nexus has their own ZKVM, and they're building their own infrastructure for generating proofs. Same with Neil. And then over here, Pato. So I haven't had enough time to look into Pato, but they have something about privacy, so worth looking into more and seeing where they fit in this space. Okay, I am blowing through time here, so I'm going to try to speed things up. All right, so this is just kind of high-level trade space performance, right? So whenever we talk about snark proving, performance is always kind of like one of the biggest things. How fast can you prove something, especially if you're talking about like an AI inference, and inference is already expensive. How much more expensive is your snark going to be proving being on top of that? So these are the different ways that people kind of handle this. So one, you can start with a custom proving system. So rather than using like Plonk with KZG, you can kind of design your own proving system from the ground up to be super performant for the specific computation that you're trying to prove. And so Modulus Labs has done this with for ML proving. So they just published a paper on this proving system remainder, which is like tailored specifically to the types of computations that they want to prove. Pretty amazing stuff, right? So, but pretty deep in the stack. It's like at the base layer of your stack. Then when you go like kind of one up, you have your proving system, and then now what types of circuits are you trying to prove? So you have guys like RISC-0, Nexus, the ZKVM crew, who are all building basically ZKVMs, making it easy for people to develop applications that use zero knowledge, right? So you write your code like you would normally write code, compile it to your ZKVM, and then now you can prove that code is executed. So general purpose, very easy to use, but it's not going to be as performant as like an application-specific proving circuit, right? So this is kind of like what Axiom is doing. So Axiom is creating a framework where people write circuits and making it easy to write circuits that might be faster than than just proving with a ZK VM. There's other things, right? So we've got this infrastructure, these infrastructure groups who are building, different provers. Like, is your prover modular? Like, can you swap out one proving system for another? Can you swap out Starks for Planck, say? So it's an important consideration. And then always, like, this whole thing is getting proof back on chain, right? And so how expensive is your smart contract verification? Another one interesting here, like data availability. So similar how you have like data availability problems with L2s, you have the same kind of data availability problem here, right? The problem is to verify your expensive calculation, you need your input data, right? So you need this input data and the output data to end your proof, right? You need all this data to be able to actually prove or to actually run your verify algorithm. So if this input is very large, that's going to be pretty expensive. So you probably have similar, so then there's also similar solutions you could use for data availability, right? Maybe just kick off all the data, somebody attests to that data, and then, attest to the data, and then, do your verification, assuming that attestation is correct. So things you can do here, similar to what L2s are doing. Okay, so now the graph in 3.5 minutes, the other half of the presentation. All right, so for those of you who are familiar with the graph is a decentralized blockchain data indexing and querying protocol. And so, yeah, big thing here is decentralized, right? This is just an cute little figure showing, kind of what the indexing process looks like. Say you've got your contract, emits a bunch of different events. This is how the events get emitted on the blockchain. It's a mess. If you want to be able to access your events, you want, all your yellow events, you need a write indexer to index all the stuff for you. The graph does this for you, right? Sets up the blocks, makes indexing easy for you. The graph is live, right? So the graph is running. This past quarter 4, saw almost 1 billion queries. So it's out there, it's being used. And then here's an important thing, at least to me, the graph is a blockchain network. So here I'm borrowing phrases. Specifically, like what a blockchain network means is the graph can make strong commitments about future behavior, right? So the graph isn't a company. It's not a company that might shut down if it doesn't get funding, right? The graph is a blockchain network. It has a token. It has incentives for indexers to be producing and doing what they do. So as long as the protocol is live, as long as indexers are working, the graph will exist, right? So that's an important thing here. And then the final thing here is the graph is a blockchain coprocessor. And I have an asterisk here because currently it has high trust assumptions. And so let's dig into this, like the graph is a blockchain coprocessor. The first time that I really kind of saw this idea was in Brandon, one of the co-founders of the graph, his Graph Day talk in 2022. He called it a read-oriented roll-up. So basically, right, reading data from the blockchain, doing some processing on it, so your query transformations, and then returning that data to the consumer. Yeah, and so currently the graph supports GraphQL queries, so that's the type of like computations that you can do on the historical data. Soon we're going to SQL and more, right? And so I have a little link here if you can access the slides. Go to this link and check out this talk at Datapalooza by Adam Fuller. Okay, so the graph is a blockchain coprocessor with high trust assumptions. So the graph started out like many decentralized networks do, as centralized, right? And we're progressively decentralizing, removing points of centralization. And one of the points of centralization is the way that we verify that data is correct is we have an arbitration council who basically manages disputes. So if somebody suspects an indexer of serving bad data, you kick off a dispute with the arbitration council, and then the council decides who is correct here. And so in the blockchain coprocessor space, we could say the graph is a blockchain coprocessor with trust in an authority, a trust in that arbitration council. And so the big thing here is lowering trust assumptions. It leads to greater composability, stronger commitments, and enables stronger commitments about future behavior. So that's what we want to remove. We want to remove arbitration council. We want to be able to provide stronger commitments. We want to make it easier to integrate and put less trust in humans and more trust in math. Yeah, so this is just kind of like the outline. We're going to build a snark. These are the types of things that we need to prove. One, we need to prove that the historical data is correct. So this is like Axiom historical data proofs. This is showing data came from the blockchain. Another big thing is proving that no data was excluded, right? So we're indexing data. If you're trying to build a pricing oracle based off of swap events, if you can skew your oracle by emitting data, right? So you can still prove all the data is correct, but you've skewed it by excluding data. So we can't allow that, right? We need to prove that no data was excluded. And then any computation that you do an average. You need to prove that average was done correctly on the data. And then other things for the graph that's a requirement, right? Is all of our provers need to be open source, and because we're a decentralized network, everything that we do is open source. Everything that we publish, everything that we put out, it's all open source, it's all available. We're decentralized. It's an unstoppable blockchain network, right? And so the proving system needs to be able to integrate with that type of network. And then queries, we're serving queries with high throughputs, so our proving systems need to be able to keep up with that. And then modularity is actually pretty important here. So we're not going to be able to snark prove everything, and we probably shouldn't snark prove everything. We should be able to have different proving systems for different customers, right? Because different customers have different requirements and all that stuff. So yeah, these are features of the system that we get out of the graph by improving the trust assumptions. And yeah, where are we now? We're currently in the design phase, right? And we're focusing on proving kind of arithmetic queries. So rather than proving GraphQL queries or proving SQL queries directly, we're proving arithmetic queries, like a sum, an average, that type of thing first. Yeah, and we want to ultimately, right? We want a ZK snark-based solution that we can verify on-chain with trustless. And so that's where we're working. If you think you can work with us, or if you're interested in this, reach out. Let's talk. That's all.